Hello everybody, welcome to this lesson. Today I'm going to discuss a special topic in physics, an area of astrophysics, which of course has something to do with stars and all the celestial bodies. So under astrophysics, I want to discuss the stellar evolution. It's our main topic of today. My name is Edexcel. I'm a tutor. I'm based in Kenya. Welcome. I'm going to discuss several areas. As you can see in the table of contents, just going to introduce it and introduce what stellar evolution is. Then we look at what is known as the Hertzsprung-Russell diagram, or famously the HR diagram. Then we look at hydrogen burning, spectral classes, and then we look at a few questions under the Edexcel unit, that is unit 5. So astrophysics is a branch of science, a branch of physics that is concerned with the study of celestial bodies. And the study of celestial bodies include how bodies are born, or their origin, until they get to their death. So when celestial bodies are studied, there are several physical properties that they have, which includes the luminosity or the brightness of the light that they give out, the size of the celestial bodies, the mass density, temperature, and the chemical composition in these celestial bodies. So astrophysics is primarily an observational subject because it is based on what is observed. The radiations that come from those celestial bodies are analyzed to determine their distance, the amount of light they give, and based on those two parameters, it is possible to identify the time of birth of a star, the life, and the death of a star. So all that is the life cycle of a star, which is just referred to as the stellar evolution. So to discuss this, I have some diagrams that will summarize the life cycle of a star. On the right, I have a pictorial diagram which shows the beginning of a star formation, and it goes up to the different stages until the star is considered to be dead. So there are different terminologies that I will introduce. On the left here, I have a diagram, which is the HR diagram, which has main features in it that are important to understand the life cycle of a star. So on the right hand side, the first stage is the birth of a star. The birth of a star basically means how the star comes into being. And as what a star is, for example, our sun is one of the stars. So the beginning of life of a star starts with a collection of hydrogen atoms in the space. These hydrogen atoms are basically the primordial hydrogen, which when they attract each other, there is a gravitational attraction that pulls them together, and that gravitational pull increases, and more hydrogen atoms come together. So when the pull increases even more, you have these hydrogen atoms approaching the center of the core at a very high speed, and that continues for many years until the temperature at the center becomes very high and nuclear reaction begins to take place, and the temperature of the star increases. At the same time, the gravitational pull increases. So these two reactions, the nuclear reaction at the center and the gravitational pull um, must balance for the star to be considered uh, born. So these hydrogen atoms are collecting together are known as a stellar nebula. So when the mass of such a star becomes huge enough to the point where the temperature is also high and the mass produces light, it becomes more luminous, then it gets to a stage which is now referred to as a protostar. So this protostar, at that particular point, if you look at the diagram on the left, the protostar at that point is not in the main sequence in the HR diagram until the point is reached when the gravitational pull is balanced in the nuclear reaction. So at that point, the protostar is now entering the main sequence. You can see the diagram on the left. The main sequence is the gray line. So at that point, what happens is that the hydrogen at the core of the protostar begins the nuclear process, or what we call the proton-proton burning. So that consumes about 99% of the life of the star when it is in the main cycle. So a star can remain in the main cycle for as long as that hydrogen burning is continuing until such a point when the hydrogen burning begins to reduce, and then at that instant the star is exiting or can exit the main sequence. So if I can use the diagram on my left here, immediately the star enters the main sequence, then it is considered that it is now born and the age of the star is counted from there. So it remains in the main sequence with the hydrogen burning taking place at the center. And when the hydrogen burning now reduces, or the temperature at the core reduces, then the star begins to deviate from the main sequence and the temperature at the core reduces. At that point, the star expands or becomes large in size and it heads towards the giant stage. So that continues until the point where the star is big enough, the hydrogen burning has completely been consumed, and instead of now the hydrogen burning, we now have a process of the helium process. Helium and helium atoms combining together to burn. So where if you can see my cursor, the part that is indicated, that is the point where the helium process is now burning the core, and that takes place with an increase in temperature until such a point when all the helium within the core is totally consumed. When all the helium is totally consumed, the star explodes, it loses its mass, then it now becomes a very small or a tiny star, which is now headed towards this region known as the white dwarf. So these two diagrams basically explains the entry of a star in the main sequence, the point where it's exiting the main sequence, what happens in the main sequence, that is the hydrogen burning. When the hydrogen is consumed, then you have helium burning taking process until all the helium is consumed, the star explodes, it now becomes a white dwarf, the temperature reduces, and now it is considered dead. So if you look at the diagram on my right, the red part, like I mentioned, was a protostar. So when the protostar has become stable, then it gets into the main sequence. And in the main sequence, it is now small in size. And at that particular point, we talk about the hydrogen burning taking place at the core. So that happens for all the period the star remains in the main sequence until the hydrogen at the core is reduced or is much consumed, and in the process the helium gas is taking over. So the helium burning now takes place, that is just when it is exiting the giant stage, And when the helium burning takes place, we now have this star, which is known as the planetary nebula, which is drawn in blue here. So again, that takes place with an increase in temperature for as many years as possible until the point when all the helium in the planetary nebula are exhausted. Then, like I said, the star explodes, becomes a white dwarf, becomes less luminous, reduces in temperature, and it is considered practically dead. So the two diagrams basically explains the entire life cycle of a cell. The diagram on the left is just the HR, which shows three main areas. There's a line, a diagonal line, which is the main sequence, and this is where many stars or majority of the stars lies in the main sequence, including our own sun lies in the main sequence, the point which is indicated with a dot yellow. And then of course we have on the top right, that is the giant stage. Then we have the red giant stage where the stars have become massive, they are huge, they are luminous, but they are not of very high temperature. So when hydrogen burning takes place, I mean helium burning takes place, we have an increase in temperature until such a point when all the helium is consumed and the star explodes. When it explodes, it goes lower, the luminosity decreases, the mass decreases, becomes a white dwarf, and then it's head towards the death of the star. So these two diagrams are basically a summary. So like I mentioned at the beginning, the formation of a star begins with a collection of hydrogen atoms. When you have two hydrogen protons coming together, there is a nuclear attraction that brings them together. So that nuclear attraction becomes high enough, then we have more and more hydrogen atoms collecting. When it collects, the gravitational pull also increases to a very high value and attracts many other hydrogen atoms toward the center. These atoms are approaching the center at a very high speed, and that increase in kinetic energy will make the core have very high temperature at the center. So this takes place for many years until the point where you have not just a small collection of hydrogen atoms, but you have a huge mass. You have a huge mass of hydrogen atoms, which is now giving birth to what is known as a protostar. So a protostar is now the stage where the star is now ready to join the main sequence. And before it joins the main sequence, it has to be contracting in size because of the gravitational pull. And when it contracts in size, then we talk about the balance between the gravitational pull and the nuclear reaction at the center. So by the time the star is formed and by the time it is getting into the main sequence, that takes about 10 or 30 million years before it gets into the main sequence, and it remains in the main sequence as long as the hydrogen burning takes place at the core. So different stars will exit the main sequence at different stages depending on the amount of hydrogen core at the center. So this diagram here just shows the pre-main sequence stage where the protostar enters the main sequence. And then the two diagrams on top here are basically showing what happens in the core when the collection of the protostar is in the main sequence. So the red part at the core basically shows the presence of hydrogen burning taking place. And like we said, the hydrogen burning takes place as long as the star remains in the main sequence. So hydrogen burning involves the production of helium gas. So the helium gas is now the blue part which surrounds the core, and obviously the helium gas is heavier than hydrogen gas. So after several years, we have the mass of hydrogen of helium growing and begins to fuse towards the center. So when that process begins, that is when now the star exits the main sequence towards the red giant. And when that happens, it increases in size or it expands, the temperature reduces, and the helium gas takes presence in the core. So the helium burning now substitutes the hydrogen burning, and the star exits the red giant stage, moves towards the left, where you have an increase in temperature, provided the helium is still burning, until it gets to a point when the helium is all consumed, it explodes, and then it comes to the white dwarf stage, where it is heading towards its death. So the diagram on the left here simply shows the star in the main sequence. The diagram on the right here simply shows the star when it is exiting the red giant stage and it is burning towards the blue stage of the high temperature region. So the hydrogen burning is basically a three steps process, where first of all you have two protons of hydrogen coming together to produce another hydrogen atom with an electron with some energy. And then we also have another proton attacking the proton that is produced until we get helium. So the entire process begins with two protons, but we end up with helium and two more protons. That's why it is known as proton. So you begin with two protons, you end up with two protons and helium gas. So this is what takes place as long as the star is in the main sequence, and is in the main sequence until when we have now in excess helium taking over the hydrogen at the center, and now the hydrogen burning stops, and then we begin having the helium burning taking over. So in the HR diagram, we have different temperature. The temperatures are given spectral class letters from O to M, where O is the class with the highest temperature from 30,000 to about 50,000 kelvins. Then M is a class with the lowest temperature from about 2,000 to 3,500. But more importantly, we need to know the position of our sun. Our sun is one of the stars in the main sequence, is in class G. So the temperature of the sun is basically between 4,500 to 6,000 Kelvin, and it is yellow in color. So just also to mention is that in the HR diagram, there are several other stars. It's not only the sun. So our sun at the moment is currently within the main sequence. So that is just about it. So at this point, it is just good to look at some of the questions that come in Edexcel exams, especially unit 5, because unit 5, this is where we have astrophysics. The first question is simple. You're only being told to give a reason why blue-white star is much hotter than a red star. So this question requires understanding of the Wien's law, where you have peak wavelength and you have intensity of light. And what happens is that the peak wavelength is inversely proportional to the temperature, so that blue color, which has the smallest wavelength compared to red, is matched with the highest temperature because of the inverse proportional nature. And then of course we have the red star, which is the longer wavelength star, is associated with a smaller temperature. So that's what happens. But a diagram that explains this behavior can be shown, and I think I'll be able to show you down here. So this is number 2. So you see this kind of a diagram where you have the peak wavelength. We have two curves. The upper curve is the one with the highest temperature. The lower curve has the lowest temperature, but the peak is shifted towards the left. So towards the left, we have a shorter wavelength, then towards the right, we have a higher wavelength. So you definitely see that the upper curve, which is a higher temperature, is associated with the lower wavelength. And this is now the Wien's law taking shape in form of a diagram. So the second question was simply asking us to draw the HR diagram. So like I said, the HR diagram must contain the important features, and one of the important features is a main sequence, which is usually in the diagonal form, but not exactly straight. Just need to know the shape, which is a curve. And then on the bottom left, we have the white dwarf, which is the aging star, the star that is coming towards the end. And then on the bottom corner, bottom right, sorry, top right, we have the red giant stage, which are stars that have exited the main sequence stage and have grown large in size, and the helium process of burning takes effect until the star blows out and goes into the white dwarf stage. So the y-axis column basically shows the luminosity or the amount of light emitted by the star. So we have the top part, which shows the stars that are very strong in light, and then at the bottom part we have stars that are not very bright or the luminosity is low. Then the x-axis is interesting because the temperature is not increasing towards the right, but the temperature is increasing towards the left. So towards the left, you have the highest temperature, and then going towards the right, you have the lowest temperature. So those are some of the features that somebody must remember when you are drawing the HR diagram. And then, of course, the last question was talking about explanation of the formation of a star. So in the formation of a star, there are certain key points that somebody must remember is the beginning of formation of that star, which is collection of hydrogen atoms because of the gravitational attraction will increase and will attract many and many atoms of hydrogen until the mass of the hydrogen becomes big enough, the temperature at the core becomes high, and um, at that point, the protostar begins to shrink in size until we have the nuclear reaction at the center balancing the gravitational pull. And when that takes place, then the protostar is ready to join the, the main sequence, and that is the formation of a star. So the important points are listed there, and somebody can just pick up the points for remembering. And that marks the end of the lesson today. In case you have a question, you need assistance in terms of tuition, you can reach out to me. My email address is provided, and I've also provided my telephone number for those living in Nairobi, Kenya. And for those who are not in Kenya, you can still get me through the contacts, and we can do the online lectures together. Thank you very much for listening, and have a nice day.